Assalamualaikum dear students, I hope you all are fine and in the best conditions of your health. In today's lecture for the course of organic reaction mechanism, today we shall study about the activation and deactivation of benzene ring by different substituents. The key concepts which we shall discuss here will be the electrophilic aromatic substitution reactions, activating groups, deactivating groups, orientation of groups on the substituted benzene ring. So you know that benzene ring has pielectronic density, right? Because of the pielectronic density of the benzene ring is highly electronically rich system, right? So since benzene is electronically rich, it always attracts something which is electronically deficient towards it, right? So that's why benzene preferentially undergoes electrophilic substitution reactions. So why electrophile? Because electrophile is electronically deficient and benzene is electronically rich. But why does benzene not undergo addition reaction? Because benzene has resonance stability, right? And this resonance stability is very important for benzene ring. In case if a benzene ring undergoes addition reaction, then the aromatic stability of the benzene ring will be lost. So benzene cannot afford to lose its aromatic stability. Therefore, benzene undergoes substitution reaction in which one of the hydrogen of benzene ring is substituted by any other group. And in this way, by undergoing substitution reaction, benzene retains its aromatic character. Right? So next comes the activating and deactivating groups. So in the previous lectures, as you have studied, that any group on the benzene ring which accelerates the rate of reaction, which increases the rate of reaction, is called the activating group, right? So any group on the benzene ring which increases the rate of reaction of the benzene ring is called activating, while any group which decreases the rate of reaction on benzene ring, such groups are known as deactivating groups. So since we are considering the electrophilic aromatic substitution reactions, therefore any group which increases the rate of reaction of electrophilic substitution will be considered as activating groups, and any group which decreases the rate of electrophilic aromatic substitution will be considered as deactivating group, right? So in general, when we introduce an electron-withdrawing substituent on the benzene ring, right? So such an electron-withdrawing group that decreases the electrophilic substitution reaction to a very large extent, right? So what is this electron-withdrawing group doing? The electron-withdrawing group which is attached on the benzene ring, it is attracting the electronic density from the benzene ring. Right? Just remember that we want here an electrophile, right? So we want to bring an electrophile on the benzene ring. Why? Because this benzene ring is electronically deficient, is electronically rich. Since the benzene is electronically rich, the pielectronic system will easily attack on this electrophile. But the problem is here we have now introduced an electron withdrawing group. So this electron withdrawing group is decreasing the electronic density from the benzene ring, and this electronic density is being shifted from the benzene ring to this nitro group. As a result, the electronic density on the benzene ring has reduced. Since the benzene ring has less electronic density, therefore it is unable, or it is less likely to attack on this electrophile, right? That's why we say that whenever there is an electron withdrawing group attached to a benzene ring, then the electrophilic substitution reaction is reduced, right? The rate of reaction of aromatic substitution is reduced. Whereas, in case if we incorporate an electron donating group, right, then the rate of electrophilic substitution reaction increases. So for example, here we have a methyl group here. So you know that methyl group, it donates the electronic density on the benzene ring. So since the benzene ring has higher electronic density now, so the electrophile, if it comes, so this benzene ring will readily attack on this electrophile, right? So in case if we want to generalize the rate of reactions, then you can say that electron withdrawing group decrease the rate of reaction, while benzene ring is in the center, while electron donating group increase the rate of reaction. Now, you might consider that what are the factors that contribute to the activating or deactivating nature of the substituents, right? So what makes these substituents to activate the benzene ring or deactivate the benzene ring, right? Also, it may also comes to your mind that how do these substituents make a monosubstituted benzene ring more susceptible to reaction or less susceptible to reaction, right? It means that which group should be present on benzene ring which will further increase the rate of reaction or decrease the rate of reaction, right? So we understand the basic concept that how we can increase the rate of reaction or decrease the rate of reaction. We can carry out the reaction or we can make the product which is according to our demand, right? So the electronic influence of any substituent is determined by inductive and resonance effect, right? So whether a substituent will donate electronic density or withdraw electronic density, so its electronic effect is dependent on the inductive effect as well as resonance effect. So you remember that inductive effect occurs through sigma bond. You also know that inductive effect decreases with increase in distance, right? And is mostly determined by the relative electronegativity and polarization of the bond, right? So if the electronegativity is higher, the inductive effect will be more pronounced. If the polarization is more, inductive effect will be more pronounced. And just for your revision, just remember that inductive effect cannot operate beyond 3 bonds. So inductive effect dies after 3 bonds, right? Whereas the resonance takes place through pi bond. So the resonance is long range effect, right? The resonance effect will carry on, will go on until there is conjugation. So if a conjugation is through hundreds of bonds, the resonance effect will go through hundreds of bonds, while the inductive effect is operational only through 3 bonds, right? So this is the factor that any substituent, if it's attached on the benzene ring and you want to predict whether this will withdraw electronic density or donate electronic density, then the electronic effect of that substituent is determined by the inductive effect and resonance effect. So just keep in mind that inductive effect operates through sigma bond, inductive effect is distance dependent, and inductive effect is influenced by the electronegativity difference of the atoms, whereas the resonance effect takes place through pi bonds and is of long range coupling, right? The resonance effect is more pronounced in case if you have charged system. So if there is a positive charge, resonance effect will be more stronger. If there is a negative charge, resonance effect will be more stronger, right? So let's look at effects of typical groups which have inductive, positive I and negative I inductive effect, right? So we'll consider the substituents that can donate with respect to inductive effect and that can withdraw with respect to inductive effect. Let's consider firstly the alkyl groups. Alright, so in alkyl groups we will take example of methyl. So this alkyl group such as methyl, if it's attached to the benzene ring, so these are electron donating because of inductive effect as well as because of hyperconjugation. Now we have another group, this is trifluoromethyl group. So you can represent trifluoromethyl group as CF3, right? So this trifluoromethyl group, since it has carbon with 3 fluorine attached, or fluorine is highly electronegative. So because of the fluorine attached and these 3 fluorine attached, so this trifluoromethyl group is very strong electron-withdrawing group, right? So this trifluoromethyl group, this is electron withdrawing with respect to inductive effect, whereas the methyl groups, they are electron donating because of inductive effect as well as hyperconjugation. Furthermore, if you have a heteroatom such as oxygen or nitrogen or halogen, which is directly attached to the benzene ring, then these atoms can withdraw electronic density by inductive effect, right? Furthermore, if you have positively polarized atoms such as carbonyl, cyano, nitro, sulfonyl groups, such groups are also electron withdrawing group with respect to inductive effect, right? So in summary, we can say that inductively donating groups are alkyl groups because they can donate with respect to inductive effect as well as hyperconjugation, whereas trifluoromethyl group because of the 3 fluorines attached. Any heteroatom such as nitrogen, oxygen or halogen which is directly attached to the benzene ring. So these heteroatoms such as nitrogen, oxygen and halogens, if they are directly attached to the benzene ring, or if you have positively polarizable atoms such as those of carbonyl, cyano, nitro, sulfonyl, so these are also withdrawing with respect to the inductive effect. So just for a summary, so here we have donor atoms, so you know that this is benzene ring, and if there is directly a methyl group attached or any alkyl groups attached, so all of these will donate the electronic density, and because of their electron donation, these will increase electronic density on the benzene ring, and these effects will increase the rate of electrophilic substitution reactions. As electronic density on the benzene ring is increasing, so it becomes easier for the pi system to attack the electrophile. Whereas in case if you have a trifluoromethyl group here, or any group which is heteroatom and is directly attached to the benzene ring, for example, if you have nitrogen, oxygen or halogen, if these are directly attached to the benzene ring, all of these can withdraw inductively. Right. Also, if you have polarizable atom such as carbonyl system, so you know a carbonyl system is like this one. So this carbonyl system is partially positive because of this carbon, right, and it's partially negative. So here we have a polarizable, positively polarizable atom of chlorine which is directly attached to the carbon of the benzene ring, right? So if you have a directly polarizable positively charged atom attached to the benzene ring, it can withdraw electronic density. Similarly, this is cyano group, so you can see this is partially positive carbon, so if it's directly attached to the benzene ring, it will withdraw electronic density. So nitro is a very strong electron withdrawing group if directly attached to the benzene ring, so it can withdraw with respect to inductive effects. So this is sulfonic acid group. The sulfonic acid group can also withdraw electronic density with respect to the inductive effect. Next we have groups which can donate electronic density or accept electronic density with respect to their resonance effect. Right? So in order for a group to be donor with respect to resonance, it is necessary that such a group must have at least one electron pair capable of delocalization. Right? So if any group has to serve as electron donor with respect to resonance, it is compulsory that it must have at least one lone pair, right? So such groups include the amino groups, the oxygen groups, they can be in the form of hydroxy group or ether, and the halogens, right? So all of these groups, the nitrogen, oxygen and the halogen, these have lone pairs, they have shareable electron pairs. So these groups act as electron donor, right? So if you just consider these, the same groups are electron withdrawing with respect to inductive effect as well, right? So in the previous slide we saw that if heteroatoms such as nitrogen, oxygen or halogen, if these are directly attached to the benzene ring, they withdraw electronic density with respect to inductive effect, but these are donors with respect to resonance effect. Right, so we have the two phenomena, inductive effect as well as resonance, and both are opposing each other, right? These are donors with respect to resonance, but they are withdrawing with respect to inductive effect. So it may come to your mind that which effect will dominate, right? So whether the inductive effect will win or the resonance effect will dominate, the answer depends on the relative electronegativity of the heteroatom, and also on the ability of the p orbitals to overlap with the aromatic pi system, right? For example, the amino and alkoxy groups, right? Their electronegativity and their ability of these p orbitals to overlap with the pi system is significant, so that the resonance effect dominates, right? The inductive effect is apparent, inductive effect is present, but the resonance effect dominates because the p orbitals of these groups is much better to overlap with the pi system of the aromatic ring. So because of the better ability of their p orbitals to overlap with the pi system of the aromatic ring, so amino group and alkoxy group, they have a dominant resonance effect. Whereas in case of the halogens, the inductive effect is more pronounced. The inductive effect is more dominant because the electronegativity difference of the halogens is very significant. So since the electronegativity is very significant, therefore resonance effect is not that much pronounced as inductive effect, right? So resonance effect dominates over the resonance, inductive effect dominates over the resonance effect. As a result, see, the halogens are weak electron acceptors, right? So if you have a halogen directly attached with the benzene ring, then the halogens will accept the electronic density, although they will not significantly accept electronic density. They will still donate the electronic density, but they will still be considered as weak electron acceptors, right? So just for summary, if you consider the resonance donor or acceptor atoms, right? So resonance donor atoms include the lone pair containing atoms, right? So here we have nitrogen directly attached to benzene ring, so it has one lone pair. Oxygen has two lone pairs. So these are the halogens with three lone pairs as well, right? So all of these can donate the electronic density to the benzene ring with respect to resonance, but just remember that in case of the halogens, the electron donating effect is not much pronounced, right? So there is some inductive effect as well, although inductive effect overweighs the resonance, but still they are donor with respect to resonance effect. Right. So now we have groups that have a polarizable double or triple bond whose positive end is attached to the benzene ring. Again, we have the carbonyl system, we have cyano, nitro, sulfonyl groups. So these groups were electron withdrawing with respect to inductive effect. These groups are also electron withdrawing with respect to resonance effect, right? The groups that were previously electron withdrawing with respect to inductive effect, they are also electron withdrawing with respect to the resonance effect, right? So here, although inductive effect and resonance effect are on the same side, but resonance effect will dominate over the inductive effect, right? The inductive effect will not be that much significant as compared to the resonance effect. So how do we know? How do we know that a substituent will function as electron donor or it will act as an electron acceptor? Right, so in case if you are studying the electrophilic aromatic substitution, the answer is very simple, because the attacking species electrophile, right? So here we have electrophile which is electronically deficient. So if you can make the benzene ring electronically rich, the reaction will be faster, right? Because your attacking species is electrophile, it's electronically deficient species. So this electrophile is looking for a position which is high in electronic density. So if you can somehow increase the electronic density on the benzene ring, you can increase the rate of reaction, right? And any substituent that increases the rate of reaction will definitely donate the electronic density, right? Whereas if the electronic density on the benzene ring or on the ring system is poor, the reaction rate becomes slower, right? So we can generalize if you want to know that if a substituent is a donor or if a substituent is acceptor, just see the rate of reaction, right? So if a certain substituent increases the rate of reaction for electrophilic aromatic substitution, that substituent will be a donor. Whereas if a substituent decreases the rate of reaction, then such a substituent will be acceptor, right? So if you want to know, if you're not sure whether a substituent is acting as a donor or acceptor, just see the rate of reaction, right? So in electrophilic aromatic substitution reaction, any substituent which is increasing the rate of reaction will be a donor, and any substituent which is decreasing the rate of reaction will be a substituent. So for example, just consider these different substituents. So here we have a secondary amine, we have a hydroxyl group, then we have a methyl, hydrogen, chlorine, and so on, and here we have a nitro group. So here you can see the nitro group has a rate of reaction 6 × 10⁻⁸. So rate of reaction is very slow. Since the rate of reaction is very slow, you can see this group should be acceptor, right? Because it's decreasing the electronic density, it's decreasing the rate of reaction. Whereas if you can see this N-phenyl amine, so this is N-phenyl amine, then in that case the rate of reaction 10⁶. It's very higher, right? So this means this group is electron donating. Why is electron donating? Because it's increasing the rate of reaction, right? So whenever you have a confusion in aromatic substitution reaction, whether the substituent is donor or acceptor, just see the rate of reaction. So any substituent that is increasing the rate of reaction should be a donor, and any substituent that is decreasing the rate of reaction should be an acceptor. Okay, so here's a quick quiz for you. I suppose that you will be able to answer that. So you have to specify that which of these rings is activated or deactivated, right? You have to specify which of these groups is activating, which of these benzene is activated or deactivated for the aromatic substitution reaction, right? So that's a quiz, and you have to answer that quiz in your next lecture. Okay, so let's consider sequentially, sequence-wise. So firstly, we consider the groups that can donate the electrons by inductive effect as well as hyperconjugation effect, right? So those groups which donate by inductive effect and hyperconjugation effect, they are activating, they will increase the rate of reaction, and they are ortho-para directing, as you have seen in the previous lecture. So here we are considering the electrophilic bromination of methyl benzene, right? So here we have a methyl benzene, and this is the electrophilic bromination. So as you have studied in the previous lecture, the catalyst used for this purpose is the iron bromide or ferric bromide, and normally the solvent we use is the tetrachloromethane. So under these conditions, what happens that we get 39% of the ortho product, less than 1% of the meta product, and 60% of the para product, right? So you can see that this reaction is reduced but selective, right? It's selectively favoring the para product as well as the ortho product, whereas the meta product is in trace amount. It's virtually no meta product, right? So you can say that this reaction is only giving the para product and ortho product, right? So bromination is not only a special reaction in which we get this ratio of para product 60% and ortho product 39% with almost no meta product. So almost all of the reactions of alkyl benzene give similar results, right? And the only product we get are the ortho and para substituents. So we don't get any meta product in reactions that involve alkyl benzene, right? So it's evident that the attacking electrophile is not affecting the orientation, right? So the orientation or the directing effect is only determined by the already attached substituent. It's not affected by the electrophile, right? So you must keep in mind, just remember that the directive effect or the orientation of the incoming substituent is not affected by the electrophile. It is determined by the substituent which is already present on the aromatic ring, right? So now let's consider that why the ortho and para products are dominating while meta product is not forming at all, right? So just remember that whenever the carbocation is more stable, the product will be more stable. And if the carbocation is not stable, the product will not be stable and such product will not be formed, right? So the product which is more stable will be formed in larger amount, and if a product is highly unstable, that will not be formed at all. So here consider that this electrophile and this is a methyl group here, right? So electrophile, in case if it approaches the ortho carbon here, right, then we get a positive charge here, and there are different canonical forms. The important canonical form is this one. Why? Because here we have an electrophile, and this electrophile, next to an electrophile is a positive charge, and this positive charge is next to a methyl group here, right? So you can see this positive charge is a tertiary carbocation. You know, tertiary carbocation are stable. For this methyl group stabilizing this positive charge by means of hyperconjugation, right? So since this positive charge, since this carbocation is very stable, right, because of its stability. Why stability? Because number one, this is a tertiary carbocation. Secondly, this tertiary carbocation is being stabilized by this methyl group by hyperconjugation as well as by inductive effect, right? This positive charge is stabilized, therefore this structure is highly stable, and because this structure is highly stable, so we get ortho product as a dominant product. Now let's consider the meta product, right? So in case if this electrophile is approaching at meta position here, so you get a positive charge here, right? Positive charge here and positive charge here. You can see that all of these carbocations that are forming, they are secondary, right? The secondary carbocations are not stable as the tertiary carbocation. Now let's consider the para attack. So in case of para attack, so here we have positive charge, we have positive charge and a positive charge. Again, the most significant contributor is this one. Here again we have a tertiary carbocation which is being stabilized by methyl. So methyl is stabilizing this tertiary carbocation by means of inductive effect as well as resonance effect, right? So you can see that the carbocations that are formed by ortho attack and para attack, they are highly stable. Since the carbocations are highly stable, therefore they are formed to a larger extent. Whereas in case of meta, there is no stable carbocation formed. Therefore, the meta carbocation, the carbocation that's formed by meta attack is not stable. Therefore, the meta product is not formed at all, or if it's formed in very trace amounts. Right. So now we have studied that in case if we have a methyl benzene, then the methyl benzene is ortho-para directed. But now if you just see the relative ratios of this product, you can see that the ortho product is 39%, whereas the para product is 60%, right? So although both ortho and para products are stabilized by the stable tertiary carbocation, but why is the difference in amounts of these products that are formed? Right? So why para is being favored or ortho product? The answer to this question is the steric effect. Right? So if there is a bulky group next to the ortho position, then in that case, because of the steric hindrance, especially if the electrophile is also bulky, right? If you have a bulky substituent at ortho position, and if the electrophile is also bulky, then in that case it's very difficult for the attack to occur on ortho position, right? So ortho product is found in lesser amount because of steric hindrance, right? So if there is a methyl group, then steric hindrance is not significant, therefore you're getting almost 40% of the product. But if you are attaching some group which is much more bulkier, then this ratio of the ortho product will decrease further. Whereas there is no steric effect at para position, therefore the attack at para position is very easier, right? Therefore whenever there is a ortho-para product are formed, the para product is dominating because of the less steric effect that are operational at the para position, whereas the ortho position is sterically hindered, therefore the rate of reaction at ortho position is slower, and the product that's formed at ortho position is in lesser amount, Next category is that groups that withdraw electronic density by inductive effect. Right? Previously we saw groups that were donating electronic density by inductive effect and hyperconjugation, and now we shall discuss the groups that withdraw electronic density by means of inductive effect. So any groups that withdraw electronic density by inductive effect, they are deactivating, they decrease the rate of reaction, and they are metadirecting. Right? So here we are considering the example of trifluoromethyl group. So here it's a trifluoromethyl group. So if this trifluoromethyl group is directly attached to the benzene ring, then this group will withdraw electronic density. Right? So since this group withdraws electronic density, so benzene rings become electronically deficient. The rate of reaction with the electrophile will decrease. Right? So since the rate of reaction is decreasing, it's not easier for the electrophiles to react on the benzene ring. But if you heat this reaction, then substitution occurs, but the substitution will only occur at meta position. So there is no ortho product and there is no meta product. Right? So whenever you have electron withdrawing groups attached to the benzene ring, which are withdrawing with respect to inductive effect, so such groups will deactivate the benzene ring. What do you mean by deactivation? It means they will decrease the rate of reaction, and such groups will act as metadirecting groups. Right? So let's consider this example. So here we have trifluoromethyl group directly attached to the benzene ring. So its electron is withdrawing the electronic density toward itself. So the density on the benzene ring has decreased. Right? So you can just see the ratios. So this ortho product is 6%. This para product is 3%. So it's a very rough ratio. Right? So it's almost negligible amount, whereas the meta product is formed in 91% yield. Right? So why this meta product is formed in 91% yield while others are formed in trace amount? So you can see by seeing the relative stability of the canonical forms. So here we have ortho attack, right? So when the electrophile approaches at ortho position, you can see different carbocations here, and the important thing here is that this carbocation is next to trifluoromethyl group, right? So this trifluoromethyl group is highly electron withdrawing, right? So this withdrawing group is not able to stabilize this positive charge, right? Here we have deficiency, and this group is creating much more deficiency. So this group is decreasing the stability of this carbocation. So this is the most unstable carbocation, right? So this carbocation, since it is most unstable, so this product will not be formed, and if it will be formed, it will be formed in very less amount. Here we have a meta attack. So in case, if you can see that in meta attack, the positive charge never comes to the carbon that has this trifluoromethyl group attached, right? So as a result, so these carbocations are not much more destabilized, right? So these carbocations are not stabilized, but they are less destabilized, right? So the relative stability of the carbocation that are formed by meta attack is better than the stability of the carbocation that is formed by ortho attack. Now let's consider the carbocation that are formed by para attack, right? So if the electrophile approaches at para position, so here we have positive charge here, positive charge here, positive charge here. Again, you can see that we are having a positive charge on the carbon that is directly attached with this trifluoromethyl group. So this is electron withdrawing, and this is electron deficient center, right? So this carbocation is highly unstable. As a result of this destabilization, the para attack is not favored, right? You can see that when you have electron withdrawing groups, in that case the ortho and para isomers, the ortho and the para carbocation, they are of less stability. Because of their less stability, they are not formed, whereas the meta product, because of its less destabilization, therefore it is formed in much more amount. So here we have a quick quiz again. So you have ranked these compounds in order of decreasing activity in electrophilic substitution reaction, right? So you have to check which of these will be highly activating and which of these will be most deactivating group for electrophilic substitution reactions. Now we have the third category, the groups which donate electrons by resonance effect, right? So as you have studied in the previous lectures, the groups that donate electrons by resonance effect, such groups activate the benzene ring for electrophilic reaction, and they are ortho-para directing, right? So benzene rings, which have the amino groups or the hydroxyl groups directly attached, they are highly activating, right? They are strong electron donating groups, and they activate the benzene ring towards electrophilic substitution reactions, right? So just for your understanding, you can see that if we have phenol or if we have an aniline group, then when we carry out the electrophilic substitution reaction, we don't even need a catalyst. So these reactions are very rapid, and these reactions do not stop at single substitution, but instead, for example, if we have an aniline, we carry out bromination. Just see, we are not using any catalyst, and we don't get monobromo product, instead we get tribromo product. So we have substituted all the three possible positions. So we have substituted ortho as well as para position, and the yield is 100%, right? Similarly, if we have a phenol, again there is no need for catalyst. The reaction occurs at room temperature very rapidly, and we get 100% of tribromo product. So we cannot get a monobromo product. So these groups of amino group or the hydroxyl group, they are very strongly activating. They increase the rate of reaction of the electrophilic substitution reaction, and they are very strong electron electron donating groups, and they are ortho-para directing groups, right? So in case if you want to get a mono substitution, right, in the previous slide you saw that in case if we have an amino group or hydroxyl group, we cannot get a mono substitution. But if you want to get a mono substitution, then you have to modify this amino group of hydroxyl groups, right? So we can convert this amino group into an phenyl acetamide group, or we can convert the hydroxy group into methoxy group as well, right? So if we modify these groups, then we can get a mono substituted product. How? For example, so in this case we have converted the aniline, the amino group, into this acid amino group, right? So we have converted in this amino group into amide group. So because of this amide group, now the nitrogen has become deactivated, right? So nitrogen has the activity of the nitrogen has decreased because the lone pair is involved in resonance here, right? So the lone pair is involved in resonance with this carbonyl system. As a result, the electron donating effect of the nitrogen has decreased, right? So since electron donating effect of nitrogen has decreased, therefore the rate of reaction will also decrease, right? So in this case, you can see that the rate of reaction has increased, that has improved, but we are getting only mono substituted products, right? In case if you're not modifying these groups, we will get the tri-nitro group, we will get the tri-nitro product. But in case if you have modified the amino group, in that case we will get the mono substituted products here. So we get nitro group 21% here, the matter is in trace amount, while the para product is dominating with 79% here, right? So why the para is dominating, not ortho? Because of steric effect, right? Because we have a very bulky group here, so it becomes difficult for the nitro to approach this position. So it's easier for the nitro to approach this position because it's far away from this sterically hindered group. So we are getting the para product as a major product, while the ortho is forming as minor product, while the nitro group, the beta group, is being formed in a very less amount. So we can see the relative stability of the carbocation in this reaction as well. So you can just see that when in case of the ortho attack, so here we have a carbocation here. So you can see this is positive charge. Although this positive charge is next to an electronegative atom, which is nitrogen, but nitrogen is capable of electron donation, right? This positive charge is being stabilized by resonance of electron donation of this nitrogen group, right? So this is a stable carbocation. Because of this electron donation of resonance, this carbocation is being stabilized. While in case of meta attack, no such stabilization is possible. Similarly, in case of para attack, here we have this carbocation. This carbocation is being stabilized by electron donation of this nitrogen group, right? So what we get a carbocation, we get a system which is stabilized by means of resonance, right? So this is a very, very stable resonance structure. Similarly, we get a very strong resonance structure, very stable resonance structure by means of ortho attack, right? So for that reason, the ortho and para attacks are favored, and the products are formed by ortho and para attack, whereas the meta attack does not result in formation of any stable carbocation. Therefore, the meta attack is not favored, right? So next category is the groups which withdraw electrons by means of resonance. So whatever the groups which withdraw electronic density by means of resonance, they decrease the rate of reaction for the electrophilic substitution reaction, means they will deactivate the benzene ring, and they are meta directed, right? So there are several groups which deactivate the benzene ring by means of resonance. For example, carboxylic acid group, right? The carboxylic acid groups, they deactivate the benzene ring because they withdraw electronic density, right? So because they withdraw electronic density, so it becomes difficult for the electrophile to approach the benzene ring. Just for example, if we compare the rate of nitration of benzene and benzoic acid, so the rate of nitration of benzoic acid takes place 1/1000 times, means 1000 times slower than the rate of nitration of the benzene ring, right? So this is the difference in reactivity. So benzoic acid reacts 1000 times slower than the rate of reaction of the benzene for nitration reaction, right? So the benzoic acid yields meta product as the dominant product. Here we have a benzoic acid, and under these conditions, so we have to heat the reaction, right? So if we don't heat the reaction will not occur because this group is deactivating benzene ring. It's not allowing the benzene to react. So if you want to react the benzene ring with electron withdrawing groups, then you have to heat the reaction, right? So under heating conditions, what we get 80% of the meta product, 18.5% of the ortho product, and about 1.5% of the para product, right? So these are the statistics, and why we are getting the dominant meta product. Again, the reason will come from the relative stability of the carbocation here. So in case of the ortho attack, the carbocations that are formed, the most important carbocation is this one, right? You can say here this carbocation, which is deficient center, is next to a group which is also deficient. So here we are having two deficiencies together. So this carboxylic acid group is decreasing the stability of this carbocation, right? This carboxylic acid group is destabilizing this carbocation. So as a result, this carbocation is highly destabilized. So the ortho attack is not favored. In case of meta attack, there is no such carbocation which is highly destabilized, right? So these are less destabilized carbocation, right? So meta is not stabilized carbocation. Meta attack is not forming any stabilized carbocation, but it is forming less destabilized carbocation. That's why meta attack is favored. Again, if you check for the para attack, in case of para attack, so again we are having a positive charge next to this carboxylic acid group here, right? So if you just draw the resonance form, you can see we are getting two positive charges together here, right? So since two positive charges are together, so this is highly destabilized carbocation. So since the carbocation is highly unstable, therefore the ortho and para attack are not favored with electron withdrawing groups which withdraw with respect to resonance, right? So these groups are meta directing groups. Now if we have another case, so there's always an exception, which is the halogen substituents, right? So halogen substituents, in the start we saw that halogen substituents have a dominating inductive effect, and they are withdrawing with respect to inductive effect. So halogens are withdrawing with respect to inductive effect, so they are deactivating the benzene ring. However, although they are deactivating the benzene ring, they are still ortho para directed, right? So far we have studied that any group which is deactivating is always meta director, any group which is activating is also ortho para director. But the halogens are exception. Although they are deactivating groups, they decrease the rate of reaction, but still they are ortho and para directing groups, right? So the resonance effect is not dominating, so it's the inductive effect that dominates, but still there is electron donation, and because of the electron donation, we get ortho and para product instead of the meta product. So here we have a bromine here, which is attached to this benzene ring. So bromine is a halogen, it's electron withdrawing with respect to inductive effect, right? So although its electron withdrawing inductive effect is dominating, but still it donates the electronic density, right? So its rate of reaction will be slower. Although rate of reaction will be slower, but it will give the ortho and para product. It will not give meta product too much significant amounts. Just see the ratio. So in case of ortho product, the ortho product is 13%, the para product is 85%, and the meta product is just 2%. It's forming in the trace amounts, right? So again, so you see that why the ortho and para product is dominating. The reason is the resonance stability of the carbocation here. So in case of ortho attack, we are getting different secondary carbocations, but this carbocation is special because this carbocation is next to a halogen. Although halogen is electron withdrawing, but this halogen can donate electrons because of the lone pair. So this lone pair can stabilize this positive charge, right? So because of the stability of this positive charge by means of lone pair of halogen, so the ortho attack is favored because the carbocation is stabilized. In case of meta attack, no such stability is found. In case of para attack, again, we get the carbocation which is stabilized by lone pair of this halogen, right? So this is the way in which all the halogens are electron withdrawing with respect to inductive effect, but still they tend to donate electronic density by means of resonance effect, right? So halogens are exceptional because they are the only groups which are deactivating the benzene ring, but still they are ortho para direct, right? So here we have a summary here. The activating groups, whether they are activating the benzene ring by means of inductive effect, resonance effect, or the hyperconjugation, they always direct the electrophile to ortho and para positions, whereas all the deactivating groups, they direct the incoming substituent to meta position, right? This statement is true for all substituents except for halogens. So halogens are deactivating by inductive effect, but instead of meta director, they still give the ortho and para product, right? Why? Because they stabilize the positive charge by means of resonance, right? So that's all for today's lecture. I hope you have understood it well. Thank you for your patience.